Welcome to this lesson on the reflection of light by curved or spherical mirrors. We will explore key terms, how images are formed, and real-life uses of curved mirrors. Curved or spherical mirrors are special mirrors shaped like a section of a sphere. There are two main types: concave mirrors, which curve inward, and convex mirrors, which bulge outward. Concave mirrors focus light inward and are often used in telescopes and shaving mirrors. Convex mirrors spread light outward and are used in vehicles for wider rear views. These mirrors play important roles in science, safety, and technology around us. Every spherical mirror has key parts you should know. These are: 1. The pole. 2. Aperture. 3. The center of curvature. 4. The radius of curvature. 4. The principal axis. 5. The focus. 6. Focal length. We will now look at these terms individually. First, the pole. The pole, represented by the letter P, is the center of the curved mirror surface. It serves as a reference point when drawing ray diagrams. The aperture is the width of the mirror's reflective surface, often represented as AB. It affects how much light the mirror can gather. Next, we look at the center of curvature. The center of curvature, C, is the center of the imaginary sphere from which the mirror is cut. The distance from the pole P to C is called the radius of curvature. The principal axis is a straight line that joins the pole P to the center of curvature C. The principal focus, F, is where parallel rays meet or appear to come from after reflection. The focal length, denoted as F, is the distance between the pole and the principal focus. It is equal to half the radius of curvature. To understand how images are formed by curved mirrors, we must first consider two things: the mirror type and where the object is placed. Concave mirrors form different kinds of images depending on object position. Convex mirrors, however, always form virtual and diminished images. We use ray diagrams to predict image characteristics such as size, orientation, and position. Let's now examine how images are formed in different object placements. When the object is placed beyond the center of curvature, the reflected rays converge between the center and the focus. This forms a real image because the rays actually meet at a point. The image is inverted and smaller than the object. This principle is applied in devices like telescopes. Ray diagrams clearly show this convergence beyond C. If the object is positioned exactly at the center of curvature, the image is also formed at that point. This image is real and inverted, just like in the previous case. However, the image has the same size as the object. This scenario is ideal for demonstrating symmetry in spherical mirrors. It's a clear example of how image position matches object position. Placing the object between the center and the focus results in a larger image. This image forms beyond the center, and it is both real and inverted. This magnification is useful in applications like projectors or spotlights. The closer the object moves toward the focus, the larger the image becomes. It's important to use ray diagrams to visualize this change. When the object is placed right at the principal focus, something interesting happens. The reflected rays travel out parallel to each other. Because the rays never meet, no image is formed at a finite distance. we say the image is formed at infinity. This behavior is important in focusing light beams in devices like searchlights. When the object is placed between the focus and the pole of a concave mirror, the rays appear to diverge. They seem to originate from a point behind the mirror. This forms a virtual, upright, and enlarged image. This setup is commonly used in shaving mirrors and makeup mirrors. The image appears behind the mirror and cannot be projected onto a screen. Unlike concave mirrors, convex mirrors always form the same type of image. Regardless of the object's position, the image is always virtual, upright, and smaller. This image appears behind the mirror. Convex mirrors are widely used as rear-view mirrors because they give a wider field of view. Their predictable image formation makes them useful for safety and surveillance. Parabolic concave mirrors are used in car headlamps and searchlights to produce focused beams of light. Convex mirrors serve as driving mirrors because they provide a wide-angle view of traffic behind. Concave mirrors are often used in shaving mirrors to magnify the face clearly. In astronomy, large concave mirrors are found in reflecting telescopes to gather and focus light from stars. They are also essential in solar ovens and some solar water heaters to concentrate sunlight for heating. Each of these applications uses the reflective properties of curved mirrors to control light direction. The shape of the mirror determines whether the image formed is real, virtual, magnified, or diminished. These diverse uses make curved mirrors vital tools in science, technology, and daily life. Let's take a moment to test your understanding of what we've covered so far. Please choose the correct answers to the following questions. In summary, curved mirrors reflect light in unique ways depending on their shape and the object's position. Understanding these principles helps in their practical applications in everyday life. Thanks for watching. To deepen your understanding of any topic, explore our comprehensive resources, including revision notes, past questions, gamified quizzes, and workbooks. These tools are designed to help you master the concept effectively and enjoyably.